You think chaos means no rules? Look at turbulence. Water crashing over rocks, smoke rising from a cigarette, twisting and folding into impossible shapes. The stock market, on a bad day, prices jerking up and down without any apparent reason. Weather systems colliding, forming hurricanes that seem to appear from nowhere. Chaos, disorder, randomness, the complete absence of pattern. That's what everyone believes. That's what the word chaos means to most people. If something is chaotic, it has no rules. If something is random, there's nothing to understand. Chaos is the opposite of order, the absence of structure, the void where science cannot reach. Wrong. Chaos has rules. Chaos has structure. Chaos has a kind of order so deep, so universal, so mathematically precise that once you see it, you realize we've been completely misunderstanding what chaos actually is. I spent my career finding order inside chaos, not despite the chaos, but because of it. And what I discovered is that chaos isn't the enemy of pattern. Chaos is where pattern hides. Chaos is where the deepest regularities of nature reveal themselves to those who know how to look. Let me show you what I mean. Start with something simple. A dripping faucet. You know the sound. Drip, drip, drip. Regular, predictable, boring. Now open the faucet a little more. The drips come faster, still regular, still predictable. Keep opening it, and at some point something strange happens. The dripping becomes irregular. Sometimes two drips close together, then a pause, then three drips, then a long gap. The rhythm breaks down, it becomes chaotic. Most people shrug. The faucet is just broken. There's no pattern anymore. Nothing to understand. But if you actually measure the timing between drips, if you plot it carefully, if you look at the data with mathematical eyes, you discover something remarkable. The chaos isn't random. It follows rules, specific rules, rules that appear in completely unrelated systems. The same mathematical patterns that govern your chaotic faucet also govern population dynamics in ecology. The same structures appear in heart arrhythmias. The same equations describe certain chemical reactions, electrical circuits, even the orbit of asteroids. How is this possible? How can a dripping faucet share mathematical structure with population biology and asteroid orbits? Because chaos has universality, different systems, completely different mechanisms, completely different scales, but the same underlying mathematics, the same patterns, the same rules. This is what I took seriously. This is what most scientists ignored for too long. The order inside chaos. Here's the deeper insight. When scientists encounter chaos, they usually give up. They call the system random, unpredictable, intractable. They move on to simpler problems, but calling something chaotic is not an explanation. It's an admission of ignorance. It's a label we stick on things we don't understand. The real question is never is this chaotic, the real question is, what kind of chaos is this? Nietzsche searched because chaos comes in families. Different systems can belong to the same family, following the same rules, even though they look completely different on the surface. Let me make this concrete. Consider turbulence. The most famously difficult problem in classical physics. When fluid flows smoothly, we call it laminar. The mathematics is clean. The predictions are precise. But when the flow speeds up, when conditions change, the smooth flow breaks down. Eddies form, vortices spin off, smaller eddies form within larger ones. The flow becomes turbulent, For centuries, scientists treated turbulence as the ultimate chaos, unpredictable, unstructured, beyond mathematical description. But look closer, measure the velocity at a single point in the turbulent flow, plot it over time, you get a wild, jagged signal. Random noise, apparently. Now zoom in on that signal. Look at smaller time scales. What do you see? More jaggedness, more fluctuations. The small scale structure looks remarkably similar to the large scale structure. Zoom in again. Same thing. The fluctuations at every scale have the same statistical character, the same roughness, the same distribution of sizes and intensities. This is self-similarity in chaos. The turbulence isn't structureless. It has a very specific structure that repeats across scales. The statistics of large eddies and small eddies are related by precise mathematical laws. This is what I call the scaling law, a rule that connects behavior at different scales. A pattern that persists across magnification. Andrei Kolmogorov discovered some of these laws for turbulence in the 1940s. He found that the energy distribution across different eddy sizes follows a precise power law, the 5/3 law it's called, a specific mathematical relationship that holds across a wide range of scales. This law doesn't tell you where each individual eddy will be. It doesn't let you predict the exact velocity at each point. The flow is still chaotic in that sense, still unpredictable in detail, but the statistics follow precise rules. The distribution of fluctuations, the relationship between scales, the overall structure of the chaos has mathematical regularity. Order inside chaos. Now here's where it gets profound. The same kind of scaling laws appear in systems that have nothing to do with fluid dynamics. Financial markets, stock prices fluctuate wildly, chaotically, day to day, unpredictable. But if you look at the statistics of those fluctuations, if you measure how big moves relate to small moves, if you examine the distribution of returns across different time scales, you find scaling laws. The mathematics isn't the same as turbulence, but it's the same type of mathematics. Power laws, self-similar statistics order hiding in apparent chaos. When I studied cotton prices in the 1960s, everyone told me the markets were random, efficient market hypothesis. Price changes follow a random walk, no structure, no pattern, nothing to find. But when I looked at the data, I found scaling. The statistics of daily price changes resembled the statistics of weekly changes, which resembled monthly changes. The same rough pattern at every time scale. Not identical, but following precise mathematical relationships. This wasn't the randomness people expected. This was structured randomness. Chaos with rules, disorder with a signature. Earthquakes follow the same pattern. The Gutenberg-Richter law describes how earthquake frequency relates to magnitude. Lots of small quakes, fewer medium quakes, rare large quakes, but the relationship follows a precise power law, a scaling rule that holds across many orders of magnitude. This law doesn't tell you when the next earthquake will hit. It doesn't tell you where. The timing and location remain chaotic, unpredictable, but the statistics have structure. The distribution of sizes follows a rule. Forest fires, same pattern, many small fires, fewer medium fires, rare catastrophic fires. Power law, distribution, scaling relationship, city sizes, many small towns, fewer medium cities, rare megalopolises. Power law, scaling, word frequencies in language, many rare words, fewer common words. Power law, the sizes of craters on the moon, the masses of asteroids, the areas of lakes, the populations of species, over and over across completely different domains, the same type of mathematical structure appears. Why? What connects these disparate phenomena? The answer lies in how they're generated. Systems that produce cascades, systems where big events trigger smaller events, systems with feedback across scales. These systems tend to produce power law distributions. They tend to exhibit scaling. They tend to have order inside their chaos. Consider how forest fires spread. A fire starts, it spreads to neighboring trees. Each burning tree can ignite more neighbors. Small fires stay small because they don't connect to enough fuel. But occasionally, conditions align. The fire finds connected fuel. It spreads and spreads. It becomes catastrophic. The same branching, cascading process. Big events are made of many small events connected together. The statistics of fire sizes emerge from this cascading structure. Earthquakes work similarly. Stress builds in fault systems. Small slips relieve small amounts of stress. But the faults are connected. Sometimes a small slip triggers another slip, which triggers another. The cascade grows. A small earthquake becomes a large one because the initial rupture connected to other stressed regions. The cascading process creates the scaling law. The mathematical structure emerges from the mechanism. This is what I mean by universality. Different systems, different mechanisms, but the same mathematical structure because they share the same cascading, scale connecting dynamics. When you see a power law, when you find scaling, you're not seeing coincidence. You're seeing a signature, a fingerprint of cascading processes, order that emerges from chaos because of how the chaos is generated. Now let me address the deepest misconception about chaos. People think chaos means unpredictability. If something is chaotic, you can't predict it. If you can't predict it, there's nothing to understand. Science is about prediction. So chaotic systems are beyond science. This is completely wrong. Chaos means sensitive dependence on initial conditions. Small differences in starting points lead to large differences in outcomes. That's the technical definition. And yes, this makes long-term prediction impossible. You can never measure initial conditions precisely enough. Tiny errors grow exponentially. Predictions become useless beyond a certain time horizon. But prediction isn't the only form of understanding. You can understand a chaotic system without being able to predict it. You can know its statistical properties. You can know its scaling laws. You can know which family it belongs to, what class of behavior it exhibits, what mathematical structures govern its fluctuations. Weather is chaotic. We cannot predict the weather more than about 2 weeks in advance. Tiny uncertainties in today's conditions grow into large uncertainties about future conditions. Long-range weather prediction is fundamentally impossible, not because we lack computing power, but because of the mathematics of chaos. But we understand weather deeply. We know the equations that govern atmospheric dynamics. We know why certain patterns form. We know the statistics of temperature fluctuations, rainfall distributions, storm frequencies. We can make probabilistic predictions. We can understand the climate even though we can't predict specific weather events. This is the mature understanding of chaos, not prediction of specific outcomes, but comprehension of statistical structure, not knowing what will happen, but knowing what kinds of things can happen and how often. The order inside chaos is this statistical structure, the regularities that persist across scales, the patterns that emerge when you zoom out from individual events and look at distributions, correlations, scaling relationships. This is what fractal geometry provides. A language for describing the order inside chaos. A mathematics of roughness that captures the self-similar structure of chaotic systems. Classical mathematics deals with smooth objects. Calculus assumes you can zoom in and find simplicity. The local approximation becomes exact at small enough scales. But chaotic systems don't simplify when you zoom in. They maintain their complexity. The roughness persists. The fluctuations continue at every scale. Fractal geometry embraces this. It provides tools for describing objects and processes that are rough at every scale. It quantifies the scaling relationships. It measures the self-similarity. It gives mathematical precision to the order inside chaos. The fractal dimension of a chaotic attractor tells you something fundamental about the system. It tells you how the chaos fills space. It tells you about the effective complexity of the dynamics. It's a number that captures structure even when prediction is impossible. When I developed fractal geometry, I wasn't trying to solve chaos. I was trying to describe it, to find the language that captures what chaotic systems are actually doing, to see the pattern in what everyone else called patternless. And I found that pattern everywhere, in turbulence, in markets, in coastlines, in mountains, in clouds, in the distribution of galaxies. The same mathematical structures appearing over and over in systems that looked completely different. This universality is the deepest order inside chaos. The fact that such different systems share the same mathematics, the fact that scaling laws appear across domains, the fact that chaos has families, has classes, has structure. Here's what this means for how you should see the world. When you encounter something chaotic, something apparently random and structureless, don't give up. Don't slap a label on it and move on. Ask what kind of chaos it is. Look for scaling, look for power laws, look for self-similarity across scales, because the chaos you're seeing might belong to a family. It might share mathematical structure with systems that have already been understood. The specific outcomes might be unpredictable, but the statistical properties might follow precise rules. This is the gift that fractal thinking provides, a way to find order where others see only disorder, a way to extract understanding from systems that resist prediction. The world is chaotic, weather is chaotic, markets are chaotic, turbulence is chaotic, populations are chaotic. Many of the most important systems we interact with are fundamentally unpredictable in detail, but they're not structureless, they're not lawless, they follow rules. Rules about scaling, rules about distributions, rules about how fluctuations at one scale relate to fluctuations at another. Finding those rules, describing those patterns, understanding those structures, that's what I spent my life doing. And what I found is that chaos is not the enemy of science. Chaos is a subject of science, a rich, structured, mathematically precise subject. The order inside chaos is not a miracle. It's not a rare exception. It's the expected signature of how complex systems actually behave. Systems with many interacting parts, systems with feedback across scales, systems with cascading dynamics, then they produce chaos with structure. They produce disorder with pattern. They produce randomness with rules. Let me close with what this means for mathematics itself. For centuries, mathematics focused on order, equations with exact solutions, systems with predictable behavior, the mathematics of smoothness and regularity. Chaos was seen as the boundary where mathematics fails, the edge of the known world. Here there be dragons, but that's backwards. Chaos isn't where mathematics fails. Chaos is where a different kind of mathematics begins. The mathematics of scaling and self-similarity, the mathematics of power laws and fractal dimensions, the mathematics of statistical structure and universal classes. This mathematics is not less rigorous than classical mathematics. It's differently rigorous. It captures different aspects of reality. It finds different kinds of order. When you look at chaos and see randomness, you're looking with classical eyes. You're expecting smooth solutions and precise predictions. When you look at chaos and see scaling, see self-similarity, see power laws, you're looking with fractal eyes. You're seeing the order that was always there, hiding in plain sight. The Mandelbrot set taught me this. That boundary, infinitely complex, apparently chaotic, yet following precise rules, the same patterns appearing at every scale, order emerging from the simplest possible iteration, turbulence teaches the same lesson, chaotic flow, but with Kolmogorov scaling, unpredictable details, but predictable statistics. Markets teach the same lesson, wild fluctuations, but with power law distributions. Individual trades unpredictable, but the overall structure following rules. The lesson is universal. Chaos has order, disorder has pattern. The absence of simple structure doesn't mean the absence of all structure. You just have to know how to look. The order inside chaos is not obvious. It doesn't jump out at you. It requires careful measurement, statistical analysis, mathematical sophistication. It requires looking at distributions instead of individual events. It requires thinking about scales instead of specific outcomes. But once you develop these skills, once you learn to see in this way, you find order everywhere. You find that the apparently structureless has structure, that the apparently random follows rules, that chaos, far from being the absence of pattern, is where the deepest patterns hide. This is what I took seriously. This is what changed how we understand complex systems. This is why fractal geometry matters, not as a collection of pretty pictures, not as abstract mathematics, but as a way of seeing the hidden order in the chaos of the natural world. The patterns are there. The rules exist. The mathematics works. You just have to look at the right scale, not comfort, not simplicity, truth,